Learning Outcome 1010. Sketch the approximate magnitude and phase of the discrete Fourier transform based on pole zero locations. In Chapter 9, we talked about finding an approximation for the magnitude of the continuous time Fourier transform based on pole zero locations of the Laplace transform. This was based on the locations of the poles and zeros in our complex plane. The procedure was to look for maxima, and maxima are going to occur where we're on the j omega axis closest to our poles. Because we have two poles, we will have two maxima. Then we look for minima. Minima will occur at the place on the j omega axis closest to a zero. We will have one of those at a frequency of 0. Then we look to see what happens to the magnitude as omega approaches infinity. Plus infinity is up here on the j omega axis. We're going to look at those distances. We're going to have a distance of infinity to our 0 and infinity to each of our poles. So we have infinity divided by infinity squared, which in the limit is 0. So as omega approaches infinity, our magnitude will approach 0. Likewise, we're going to look at what the magnitude of our Fourier transform will be as omega approaches negative infinity. We'll have a distance to our 0 of infinity divided by two distances to our poles, infinity squared. Infinity divided by infinity squared also says our magnitude will approach 0 as omega approaches negative infinity. We should also consider, does our Fourier transform magnitude ever equal infinity? This will only happen if we have a divide by 0, which means if our x is on the j omega axis, which for this case it's not. And we want to consider, does our magnitude ever have a magnitude of pure 0, minimum that's actually 0? In the limit we have 0, but that's not actually 0. And our minimum here is dependent on our distance towards 0, and that distance is not 0, so this will never be the case. So this minimum will be small probably, because we're close, but it will not be 0. With this information, we can connect the dots, and we can get a sketch of what the approximate magnitude of our Fourier transform looks like. For discrete time, we do something very, very similar. As we said in the videos for Learning Outcome 10.1 and 10.2, our j omega axis is our unit circle now. So whereas for continuous time we were looking at distances to our j omega axis, now we're looking at distances to our unit circle. We likewise want to find maxima. Maxima are going to occur at the omega value where we have this closest distance. And that's going to be at an angle about here. That's between 0 and pi over 2. We're also going to have a maxima at this angle, and that's between 0 and minus pi over 2. So a little bit greater than 0, a little bit less than 0. But notice it's the same thing, a little bit less than 2 pi, a little bit more than 2 pi. This repeats itself with a period of 2 pi, so our spectrum will repeat itself with a period of 2 pi. We also want to look for minima. Minima occur where the distance to our 0 is smallest, and that's going to be at this frequency here, which is the frequency of 0. So at a frequency of 0, we'll have a minima, but likewise at a frequency of 2 pi, we'll have a minima. We want to ask ourselves, does it ever have a magnitude of purely infinity? That would occur if our pole were on the unit circle, which in this case it's not. We want to know whether our magnitude will ever be purely 0, which will occur if our 0 is on the unit circle, which is not. Notice that unlike continuous time, we do not ask ourselves, what is the magnitude going to be as omega approaches plus and minus infinity, because we don't have that approaching plus or minus infinity situation because we're periodic on a period of 2 pi. So from there, we can sketch our approximation. Between two maxima is going to be something a little bit smaller, depending on how close they are, whether they add or don't add significantly to each other, but it's not going to be pulled down as much as a 0 will pull it down. And it's periodic on a period of 2 pi. Notice that the high frequency here is pi. 2 pi is our sampling period, 2 pi over t, 2 pi over 1. So the Nyquist frequency is pi. This is a high frequency. 0 is a low frequency. So this would be a bandpass filter or a high-pass filter. There are no high frequencies going out to infinity for the discrete time Fourier transform.